In this video we look at the work on inverse trigonometric functions, which extends the work from the mathematics specification unit M3 and is required by the further maths specification for unit 4. So we need to be able to differentiate inverse trigonometric functions, and then we need to be able to integrate functions of the form 1 over root a squared minus x squared and 1 over a squared plus x squared, and be able to choose suitable trigonometric substitutions to integrate associated functions. So the key facts are a whole string of differentiation results and associated integration results. The syllabus is quite clear that you might be required to prove these results. So, for our first example, we are going to have to prove that the derivative of cos to the minus 1 of x is minus 1 over the square root of 1 minus x squared. So, if we have y equals the inverse cos of x, and then we've got the graph there, which we have met in unit M3, that's unit 3 of the mathematics specification. And we know that if y equals inverse cos of x, that's the same thing as cos y equals x. If we differentiate this with respect to x, then we get minus sine y dy by dx. So that's a little bit of implicit differentiation, equals derivative of x with respect to x is just 1. So we've got dy by dx is minus 1 divided by sine y. But we know that cos squared y plus sine squared y is always equal to 1. So sine squared y is equal to 1 minus cos squared y. But cos y is x. So we've got sine squared y is 1 minus x squared. So that means that we know the value of sine y is either the positive or the negative square root of 1 minus x squared. But the value of y lies between 0 and pi. So the value of sine y is definitely positive. So we now know that sine y is the positive square root of 1 minus x squared. Which now gives me dy by dx must be equal to minus 1 over the square root of 1 minus x squared, as required. Moving on to the second part of the question, we've now got a curve whose equation is y equals cos to the minus 1 of 1 minus x squared. We've got to find and simplify dy by dx, and hence show that 2 minus x squared d2y dx squared is equal to x times dy by dx. So, we've got y equals cos to the minus 1 of 1 minus x squared. To find dy by dx, we're going to need to use the chain rule. We know that the derivative of 1 minus x squared is minus 2x, and we know that the derivative of cos to the minus 1 of something is minus 1 over the square root of 1 minus the something squared. So the chain rule gives me that the derivative of cos to the minus 1 of 1 minus x squared is minus 2x times by minus 1 over the square root of 1 minus x squared. If we tidy that up, we end up with 2x over 2x squared minus x to the 4. The term inside the square root has a common factor of x squared. We know that x is positive, so the square root of x squared is simply going to be x. So we can rewrite this as 2x over x times the square root of 2 minus x squared, and cancel out the x's. We've got dy by dx is 2 over the square root of 2 minus x squared. In other words, it's 2 lots of 2 minus x squared to the minus a half. So we've now got to show that 2 minus x squared times d2y dx squared is the same thing as x times dy by dx. We know what dy by dx is, so we can work out d2y dx squared, again using the chain rule. And using the chain rule, we're going to have dy by dx is 2 lots of the derivative of 2 minus x squared, which is minus 2x, times by the derivative of something to the minus a half, and the derivative of something to the minus a half is minus a half, times by the something to the minus 3 over 2. So the chain rule is going to give me 2 times by minus 2x times by minus a half times 2 minus x squared to the minus 3 over 2. And if we tidy that up, we've got 2x times 2 minus x squared to the minus 3 over 2. So we've got 2 minus x squared times d2y dx squared is going to be equal to 2x times by 2 minus x squared to the minus a half. And that's the same thing as x times by 2 lots of 2 minus x squared to the minus a half, but we know that 2 lots of 2 minus x squared to the minus a half is dy by dx. So we've got the required result there. Let's move now to a second example, which asks us, by first completing the square in the denominator, find the exact value of the integral between a half and 3 over 2 of 1 over 4x squared minus 4x plus 5. So following the instructions, we've got to start off thinking about 4x squared minus 4x plus 5. That's the same thing as 4 lots of x squared minus x plus 5 over 4. If we complete the square on x squared minus x, we get x minus a half all squared, take away a quarter. So our completed square format for 4x squared minus 4x plus 5 is 4 lots of x minus a half squared, add 1. So we can rewrite our integral as the integral between a half and 3 over 2 of 1 over 4 lots of x minus a half squared plus 1, which is the same as the integral between a half and 3 over 2 of a quarter times by 1 over x minus a half squared plus 1. Now, making a simple substitution of u equals x minus a half means that we've got du by dx is equal to 1. So dx is the same thing as du. And what's more, when x is a half, u is 0. And when x is 1.5, u is 1. So the substitution gives us the integral between 0 and 1 of a quarter times by 1 over u squared plus 1 to be integrated with respect to u. And that is now a standard integral. We know that the integral of 1 over u squared plus 1 is tan to the minus 1 of u. So we have a quarter tan to the minus 1 of u between, with the upper limit being 1 and the lower limit being 0. So substituting in the upper limit first of all, we've got a quarter tan to the minus 1 of 1, which is a quarter of pi by 4. Remember to use radians because we're doing some calculus. So that's a quarter of pi by 4, which is pi by 16. Take away a quarter times by the tan to the minus 1 of 0, and the inverse tan of 0 is 0. So we've got pi by 16, take away 0, which is pi by 16. For our final example, we have to select a suitable substitution to find the value of the integral between 0 and 1 of x squared over the square root of 4 minus x squared. Now the thing that's really causing the problem on this integral is the square root of 4 minus x squared that we have on the denominator. And this is one where it is well worthwhile investigating the possibility of making a substitution of the form x equals 2 sine theta. Because if we do that, the 4 minus x squared becomes 4 minus 4 sine squared theta, or 4 lots of 1 minus sine squared theta, or 4 lots of cos squared theta. In other words, the square root is just 2 cos theta. So we're going to make the substitution x equals 2 sine theta, which is equivalent to the substitution theta equals inverse sine of x over 2. We've got dx by d theta is 2 cos theta, so dx is the same thing as 2 cos theta d theta. When x is 0, theta is sine to the minus 1 of 0, which is 0. And when x is 1, theta is sine to the minus 1 of a half. And sine to the minus 1 of a half is pi by 6. Again, we're doing calculus, so we must be working with radian measure for our angles. So having made the substitution, the integral now becomes the integral between 0 and pi by 6. X squared becomes 4 sine squared theta. 4 minus x squared becomes 4 minus 4 sine squared theta. And the dx term becomes 2 cos theta d theta. 4 minus 4 sine squared theta is the same thing as 4 lots of 1 minus sine squared theta. 1 minus sine squared theta is the same thing as cos squared theta. We're dealing with angles that are between 0 and pi by 6, so we're definitely dealing with acute angles, and acute angles have positive cosines, so the square root of 4 cos squared theta is just 2 cos theta. So the 2 cos theta we've got on the bottom from the square root of 4 cos squared theta cancels out with the 2 cos theta attached to the d theta. So the integral is the same thing as the integral between 0 and pi by 6 of 4 sine squared theta. Now we know that cos squared theta plus sine squared theta is always equal to 1. We know that cos squared theta minus sine squared theta is always the same thing as cos 2 theta. If we now subtract the second equation from the first equation, we obtain 2 sine squared theta equals 1 minus cos 2 theta. So 4 sine squared theta is the same thing as 2 minus 2 cos 2 theta. So the integral that we've got can be rewritten as the integral between 0 and pi by 6 of 2 minus 2 cos 2 theta. The integral of 2 minus 2 cos 2 theta is 2 theta minus sine 2 theta. If we insert the upper limit of pi by 6, we get pi by 3, take away the sine of pi by 3. If we insert the lower limit, we've got just 0, take away 0. So we're ending up with a final answer of pi by 3, take away the sine of pi by 3, which is root 3 over 2.